Hello everyone. Today we will continue with our recitation class. This is the fourth recitation since we switched to online classes. And I want to solve some problems from chapter 7, the chapter that discusses steady state current. And I want to start with an interesting problem. It's a good example of a convection kind of current, not a conduction current. And the statement of the problem is as follows. This is, by the way, example 7.2. So the statement of the problem is as follows. We have a battery that can give you a voltage difference of up to 1000 volts, right? And it's connected to two plates. So there is, how can I draw it? Plate number 1 and then plate number 2, right? And two conducting plates with a short distance between them. So there's a distance d between them. I believe d is 20 millimeters, 2 centimeters. And then the radius of those conducting plates is let me see, I wrote it down somewhere, is a, right? And a equals 10 millimeters. Right? And then what happens is that this is called voltaic tube. So this is this two plates with the space between them is called photovoltaic tube. Photovoltaic tube. Meaning what happens is that if light falls on this disc, metallic disc, an electron will be emitted. An electron will be thrown out into the air, and it will accelerate until the under the electric field until it hits the other plate. This plate is called the cathode, and the other plate is called where the electrons hit are called the anode. So the cathode is the source of the electrons, and the anode is the destination of the electrons. And the assumption here is that assume that there is any accumulation of charges in the gap, in this D gap, will not affect the electric field in the gap. That's one, right? And also assume that as the electrons leave the cathode, their initial velocity, right? So what happens is that light hits the plate, and light hits the plate and gives some energy, some kinetic energy to an electron lying at the surface, near to the surface. So this electron is going to jump up from the plate and be free and move towards the anode, right? But the energy of the light hitting the plate is going to be such that this electron is going to start its life with outside the plate with a certain initial velocity. And all the electrons exiting the cathode will start with an initial velocity of 100 meters per second. Okay, so this is the statement of the problem. It's a photovoltaic tube, and now the question is, oh, and the other thing that the problem gives you is the actual current flowing in the circuit. So what happens is, because the electrons are jumping across the gap and hitting the anode, there's a current flowing in the circuit, right? And the current flowing in the circuit, call it I is 0.01 amps. So the problem asks you to find two things. A, the charge density just next to the cathode, and then B, charge density rho V next to anode. Okay, how can we find, how can we find the charge density? Let's start with A. We want to find the charge density. The charge density, you remember from the definition of J is the charge density times V. V is the velocity vector. So if we have in any point in space, region in space, some charge density rho V, and it's moving with a certain, every point in space that has charge density is moving, every part of the charge density is moving with a velocity V, right? That gives us the current. The current is the charge times the velocity. If I have more charge with the same velocity, I get more current. If I have the same amount of charge with more velocity, I still get more current, right? So it is the charge times the velocity, right? This is in vectorial form. In scalar form, it's just J equals rho V, V, right? So, right, but we don't have J in this problem, right? What we have is I, right? But since the current, we can assume that the current is uniform, you know, the light is hitting the whole plate and electrons are exiting the plate anywhere on the plate, right? You can assume that this current I is distributed over the area of the plate, right? So we know that the J equals I distributed over the whole surface area of the plate. So this is S here. S is the surface area of the plate. What is S? What is S? Well, S is pi a squared, right? It's the surface area of a circle, right? So I can now plug this back in there. So I have rho v equals, and this is vi, the initial velocity, right? So rho v equals vi, no, not vi, equals j over vi. So rho v equals I over pi vi a squared, right? And we have all the parameters. We have I being 0.01. We know what pi is. We know that vi is 100 meters per second, and we know that a is 10 millimeters, right? So it is 10 times 10 to the power minus 3 meters in SI units, right? So that's 100 times 10 times 10 to the power minus 3 is 10 to the minus 2, cancels with 100, right? 100 is 10 to the power of 2 times 10 to the power minus 2. So we end up with 0.01 over pi. That's rho v. That is the charge density right by at the cathode. Let me call this rho vc. Charge density right next to the cathode. Oh, sorry, I made a mistake. Right, so this is 10 to the power minus 3 times 10 times 10 to the power minus 3 squared. Okay, yeah, so this is 0.01 over pi, and this is 10 to the power minus 6 times 100. 100 times 100 is 10 to the power 4 times 10 to the power minus 6. It's 10 to the power minus 2, I believe. Yeah, and yeah. So this cancels clearly with this, and rho VC, right? 0.01 is 10 to the power minus 2, right? So rho VC is 1 over pi, right? Which is approximately 0.3183 coulomb per meter cubed. Okay. Part B asks for the charge density next to the anode. Okay, so we have, again, we can use the same equation, right? So but in this, J equals rho V, but now instead of the VI being the voltage at the velocity, the initial velocity as the electron exits the cathode, V now is the final velocity as the electron hits the anode, right? So this is the same relation, and this is rho V at the anode. So rho V at the anode is going to be just J, which is the same, right, over VF. So now it's a matter of calculating what VF is. We know what J is. J is I over pi a squared VF. So we know I, we know pi, we know a squared, we don't know VF. We have to calculate VF, and VF, the final velocity, and VF can be calculated from Newton's laws, right? Because we know what the force is. We know that each electron leaving the cathode is going to have an electric field. What is the electric field? Right? We said the voltage. So this is similar to a problem where we have two parallel plates with a short distance between them. So we know what the voltage is, and from the voltage we can tell what the electrostatic field in the air gap is. Right. So we know that V equals E times D. When we studied the parallel plate capacitor, that's the relationship between, or the voltage between two parallel plates. That's the relationship. So that tells me we know what D is. D is known. So E is V over D. This is the voltage, 1000 volts, and D is known as 20 millimeters. So this is 1000 volts, and this is 20 millimeters, right? And why do we need E? Because we need to find F, the force that the electron feels. The force is going to be just QE. So the force is going to be QV over, where QE here is Q, the charge of the electron. The charge of the electron is 1.6 times 10 to the power minus 19 coulombs. We know that. Right, so it's going to be QeV over D. When you know the force, we can find the acceleration, right? So acceleration, let's call it A, is just, well, A is the what should I call it? Acceleration, ACC, because the radius of the disk is A, right? So I want to use some other variable. So ACC, which is the acceleration, is just the force over the mass of the electron. So I've assumed that the mass of the electron is ME, right? And the mass of the electron is typically 9.19 times 10 to the power minus 31 kilogram. So this is a constant of nature. We know what the mass of the electron is. So that gives me, for acceleration, this formula, QE V over ME D. I won't substitute the values. I'm just going to give you the expression. But after we find acceleration, we have everything set, right? So we have the acceleration. The whole goal is to find what the final velocity is, right? And if I know the acceleration, which I know what the final velocity is. The final velocity is the initial velocity, which I know too, it's given to you, plus the acceleration times t. Right, so I'll write that down. The final velocity is the initial velocity. The acceleration is qev over med times t. Right? Everything is known here except t. T is the time it takes the electron to travel from the cathode to the anode. And we can get that time from another equation, which is the distance equation from kinematics. Right? From kinematics. This is a physics equation, right? The distance is equal to VOT plus half acceleration t squared. This is a basic physics equation. If you know the acceleration, you can find the distance using this equation. I'm not going to derive it. It should be pretty known, well known. So this allows you to calculate t. So to find t, and that's it. We found VF. So to find rho VA, here's what we need to do. First, we need to solve quadratic equation half QEV over MED t squared plus VO t equals plus D equals 0 for t, right? And this is an equation where everything is known except t. QE is the charge of the electron, V is the voltage between the plates, ME is the mass of the electron, D is the distance between the plates, VO is the initial velocity, right? Everything is known except t. We're solving for t. After we solve for t, plug in t in. We plug it here to find the final velocity. So VF is going to be VO plus QEV over MED T. And then finally, we plug it into the equation for rho V A, the charge density at the cathode, which is I over pi A squared VF. I over pi A squared VF, right? Or I over pi A squared, and then I'll just, instead of VF, I'll write in VO plus QEV over MED T, and that's it. Everything is known here. T, we found it from solving this equation. Now, the interesting thing here is that T is a quadratic equation, so T has two solutions. Which solution would you pick? So typically what you would get is you would get a positive solution and a negative solution. So you would pick the solution that makes physical sense, which is the positive solution. Right? It takes a positive amount of time to reach the anode from the cathode. Right, and this is the problem. Now we will switch to a fuse design problem. Right, this is example 7.4, and it pertains to a fuse design problem. So how do you design a fuse? You design a fuse based on a property of copper. So let's say some material, right? So you have some material, and for that material you have a conductivity, right? And then you have J equals sigma E. So what happens is that for some material, I mean, depending on the material, there's only a certain amount of current density that you can allow through a surface before the ohmic heating gets so high, gets to the extent where the ohmic heating itself melts and vaporizes the material, right? So if J gets too high, the integrity of the material itself is suffers, and it just starts melting and vaporizing. And what happens when this event occurs? That disconnects the circuit, right? That interrupts the current flow, right? And this is the basic operational principle of the fuse. So in that example 7.4, you would have, your circuit, whatever input wires and output wires of your circuit, and they'll be connected to the fuse, and the fuse will just be some copper that might look like this, right? So you'll have some surface area of the copper, and then the surface area is going to whittle down to some very thin passageway, and then it will go back up. And the idea is that if the current gets higher than a certain designed value, this passageway here in the middle is gonna heat up to the extent that it will vaporize, and it will disconnect the circuit. So let me do this in 3D. Right, something like this. Right, and then the connections to the circuit are here. Okay, so yeah, this is like how you build a fuse. And for copper, the current density that copper can withstand before it vaporizes is around 10 to the power 8 amp per meter square. So this is the maximum amount of current, 10 to the power 8 amp, that you can stack into a meter square. All right, so the dimensions here, let me give you the dimensions. The dimensions are A, B, from here to here. This transition to the thin portion is K, and then this is C, the distance of the neck, and then the distance of the fuse part that's vaporizes is D, the length, right, and the width is C. Right, that's all you need. I mean, and the other part here is symmetrical. It's the same, has the same dimensions. So we have A, B, D, K, and O. The width of the fuse is T, okay, and T. I'm not giving you C because C is the design part of this example. C, we have to design for C such that this fuse blows up at 20 amps, I believe. Right, so this is what the fuse is designed for, 20 amps, yes. Right, so we want to find C, we want to design for the fuse. The parameters are 4 millimeters, 50 millimeters, 20 millimeters, 20 millimeters, and then T is 0.1 millimeter. And then there's sigma, the conductivity of copper, which is 5.7 times 10 to the power 7. Okay, so part A asks you to design for C. right? What is C that will cause the fuse to blow at 20 amps? Well, we know, I mean, at 20 amps, we need to reach the dangerous J for copper, which is 10 to the power 8, right? So what is J? J is I over S, right? The total current over the surface. S, the cross-sectional area, is going to be, at the neck, is going to be C times T, right? So that tells me that C equals I over J T, and I know what I is, 20 amps. J is 10 to the power 8. That's the current that's required, the current density that's required to melt the copper. And then T is 0.1 millimeter, so it's 0.1 times 10 to the power minus 3. Right, so we can manipulate this a bit. Right, so the 0 here at the numerator cancels one of the powers of 10, and then I have 0.1. Oh, yeah, that's correct. Right, so 0 cancels 1 power of 10, and then I have a 0.1, so I end up with 2 over 10 to the power 6 times 10 to the power minus 3. It's 2 times 10 to the power minus 3 meter. Right, so this is 2 millimeters. So C is 2 millimeters. Contrast that with D. So the length of the fuse, the part of the fuse that is going to melt is 20 millimeters, but the thickness is 2 millimeters. If we design the fuse with those parameters, the fuse should protect at 20 amps. Right? Part B asks you for the total resistance of the fuse. So remember we said resistance, we derived this relationship is length over conductivity times cross-sectional surface area. Right? We cannot use this. We have to use this law, this result multiple times, because this fuse has multiple portions, right? So we have this portion, this rectangular portion. Let's call it R1, right? And then let me call this R2. And then the neck, I have the neck, which call it R1. And then I have the trapezoidal part, which we'll call it R3, right? So R1 and R2 are easy to find because they're regular, they're symmetric. R3 is a trapezoid, so it's slowly tapering off. It starts with a wide base and goes into a smaller top, right? So we have to do some sort of integration. What we can do is we can find the resistance of a small slice. So I can take a slice. I can take a slice of that trapezoid and find the resistance of that slice, and then I integrate. Because I mean, because integration is just summation, and each one of those slices is connected in series to the next slice, right? So I'm effectively finding an infinitesimal resistance for a small slice, and then I'm adding all the slices together, because I'm looking at it as a bunch of infinite amount of seriously connected resistance. That's the way of looking at it. That's the way you calculate the resistance for irregular objects. But let's start with the easy part. What's R1? R1 is L1 over sigma S1. What's L1? L1 is D, right? That's the length of the neck. And then I have the surface, cross-sectional surface is C times T, right? So it's going to be D over sigma C times T. I know everything. I know all the values here, right? So if I plug in the values, 20, let me plug them in. So that's 20 millimeters over sigma, which is 5.7 times 10 to the power 7 Siemens per meter. And then yeah, C was found to be 2 millimeters. 2 times t is what do we say t was 0.1, so c times 0.1 millimeter squared, right? So millimeter cancels with one of the millimeter squares, yeah, and I end up with the inverse of Siemens, which is ohms, right? So we can do this math. It turns out to be 1.75 times 10 to the power minus 3 ohms, right? R2 similarly is L2 over sigma S2. In this case, L2 is B. So it's B, and the cross-sectional area is A times T over sigma A times T. And if you plug in all the numbers, you get 2.19 times 10 to the power minus 3 ohms, right? So although the cross-sectional area here is wider than the small neck, the resistance is still slightly higher. It's double. It's almost double. No, it's not double. It's 1.75 versus 2. Right? Why is it higher? Because the B it has more length. This segment has more length, right, than the small. So B is 50 millimeters while D is 20 millimeters. So the more length you have, the more resistance you get. Okay. So that's those two easy parts. Now, what about the trapezoidal part? This is where we need to do integration. So we need to kind of redraw that part, the coordinate system. So let me do this coordinate system. Let me do my regular three-dimensional Cartesian coordinate system. So I have Z, I have Y, I have X, right? And then let me actually let me make it easier. Let me just draw a projection, and X is known to be pointing upwards from the board, from the screen. Okay, so this makes it, I don't have to draw it as 3D. I can just draw it as 2D. So now I'm going to center the trapezoid, align it with the y-axis, right? So that it's going to be centered around the y-axis. So I'm going to draw it like this, right? And this distance here is A. This distance here, what's the distance there? Distance there at the neck is C. Yeah, it's C. So it goes from A to C, dwindles down to C, right? And of course this thing has depth to it, right? So which is T, but we don't care about T. I'm looking at the projection on the from the perspective for the YZ plane. Okay. So let me draw this line, right? So, and let me draw this. Let me now calculate. Let me try to calculate some number called Z1. What is Z1? Z1 is the difference between this dotted line and the edge of the trapezoid. Right? How do I calculate that? I use trigonometry, right? And, so I need I assume this is a straight line, so I need to find the slope of this straight line from the perspective of this dotted line, right? So the slope is this distance divided by this distance. What is this? Oh, by the way, the width here is k. Okay, so what is the slope? The slope is going to be something divided by k, right? It's going to be this divided by k. What's this distance? This distance is going to be, I can write it as a over 2, because this point is a over 2, and this point is, we said c over 2. So it's going to be a over 2 minus c over 2 over k y. Okay, so this Z1 varies. Z1 depends on Y. Okay, so the small cross-section area. So if I take a cross-section here, and I want to find its remember this thing has depth in the x-axis, and I want to find the area at that point y, at y, S at y. So S at y, the cross-sectional area at y is going to be well, it's gonna be I have to take this distance times the depth. You know, the depth is t. We know that the depth is t, so t has to be there, right? And then this is gonna be, let me calculate half of it. Half of it is gonna be a over 2 minus z1. That's half of this distance, right? A over 2 minus z1, right, times 2. This is the cross-sectional area, and I just plug it in. So it's going to be a 2, a over 2. What's z1? z1 is minus a over 2 minus c over 2 over k t. So I get the surface area, cross-sectional area as a function of y is going to be, I plug in 2 and t, I end up with at minus a minus c t over k. I missed something here. Oh, the y. There's a y here, right? Y. Okay. So what is the resistance of this section, dr3? The resistance of this section, okay, for this small cross section, I can calculate the resistance, right? I can apply, you know, L over sigma s, right? The distance is what? Dx. It's an infinitesimal, sorry, dy. It's an infinitesimal distance, right? Over sigma sy. So dr3 is going to be dx over sigma at minus sigma a minus c t over k y. What about the integral now? What about the whole resistance? The whole resistance is now just the integration. Yeah, we want to sum up all those segments from 0 to k, right? We're summing up a bunch of series resistors. So R of 3 is going to be just the integration from 0 to k. I want to now take out sigma at because they are common, right? So if I imagine I multiply a here and I divide by a here to make it easier, right? So I can take out 1 over sigma at and I end up with dx over 1 minus, I took out sigma at, so I end up with a minus c over k y. Okay, and we have to evaluate this integral to find R3. Now, what is the integral of dx 1 over, dy? Why do I keep saying dx? Okay, what's the integral in general of dx over 1 minus x? I mean, you could look at an integral table, but this is easy to find. This is just minus logarithm 1 minus x plus c, some constant. We're using c there. Let me say some m constant. Okay, so what happens here is that if you differentiate ln, you get 1 over 1 minus x, right? But then you differentiate what's inside the ln, which is minus 1. That's why you need the extra minus 1 there to take care of that. And m differentiates to 0. Okay, so that means that R3 equals minus 1 over sigma at ln 1 minus a minus c over k y from 0 to k. So what's ln when y is 0? What do we get? We get ln 1. Ln 1 is 0, right? And when y is k, we get ln 1 minus, right? So let me do this. So this is minus sigma AT. So ln of 1 is 0. When y is k, I get 1 minus a minus c, so it's 1 minus a plus c, so it becomes ln 1 minus a plus c. And we know all those values, and we know how to evaluate the logarithm, so we can get the total R3. R3, if I do the math, R3 turns out to be, well, I don't want to do the math. Let me see what the textbook says R3 should be, and you can double check this. R3 turns out to be 1.216 times 10 to the power minus 4 ohms. Now, what is the total resistance? Total resistance is everything is connected in series here, right? So we have two of those big rectangles, two of the R2s, one of the intermediate neck here, and then two of the trapezoids. So one R1, two R2s, and two R3s. So it's going to be R1 plus 2R2 plus 2R3, which is going to be, if you sum them up, it will be 6.386 times 10 to the power minus 3 ohms, or 6.386 milliohms. All right, and that covers this example. Hope you can have a good understanding now how to, when you're dealing with irregular shapes and you want to find the total resistance, how you can chop up the irregular shape into smaller parts that you can then sum together in an integral. Okay, this is an important skill to practice. All right. Now, example 7.6 follows up on this same problem, but it asks for two extra things. It asks you to find the electric field in the narrow part of the fuse. So what's the electric field here? What's E here? And then B, what's the power dissipated in the neck of, not the whole thing, just the neck of the fuse, right? So for the power, I mean, we know what the current is, and we calculated the resistance. We could just do I square R, the circuit theory version, right? But the point here is I want to show you how to use the field-oriented version. Okay, right? So and this is pretty simple problem. I mean, we already have the everything we need to find those two values. So what is E? Well, we know that J equals sigma E, right? This basic formula. So we know that E has to be J over sigma, and J is the density that is required to blow the fuse, right? We want to find the field just as the fuse blows, and the power dissipated in the neck just as the fuse blows, right? So J is, we said, 10 to the power 8, right? Coulomb amp per meter squared. Right? That's how much current density copper can withstand, over sigma 5.7 times 10 to the power 7 Siemens per meter. Okay, so we end up with so this is amp over volt. Yeah, we end up with 1.754 volt per meter. So that's the field that occurs at the neck, inside the neck, when the fuse is just about to disconnect. Right? What about the power dissipation? Well, we did find the equation for the power dissipation, which was I mean, it had many. We expressed it in different ways. It was essentially either sigma E squared, so we could use the E that we found, or it could be expressed as J squared over sigma, right? So let's do J squared over sigma. J squared is 10 to the power 8 squared over sigma, which is 10 to the power 16 over 5.7 times 10 to the power 7, which turns out to be 1.754 watts per meter cubed. Oh no, times 10 to the power 8, right? Watts per meter cubed. 10 to the power 8, that's a large amount of power, right? But it's distributed over a whole meter cubed, which is, I mean, a meter cubed of copper is a lot of copper, right? So that's like hundreds of, like over 170 megawatts, right? In a meter cube, remember, I mean the volume of the neck is much smaller than a meter cube. So what is the power that is lost in the neck of the fuse, just as the fuse is disconnecting? Well, it's the power density times the volume. Power density is, we calculated it, the volume at the neck is going to be T times C times D, right? So remember, we had the neck here, so this is T, this is C, and D is how long the neck is, right? So this gives me the volume. I have all those numbers, I plug them in, and I end up with this amount of power dissipated in the fuse, right? So it's a small number, right? But it's still not zero. I mean, it is still substantial. So even at, if we are running at currents less than the protection currents for the fuse, fault currents for the fuse, we will get less dissipation than that, but there will still be some dissipation. Okay. So fuses are lossy. I mean, they will lose some power. They will heat up a little bit. We're sacrificing some of the efficiency by not maintaining the large cross-sectional area of the copper. We kind of like going down to a small bottleneck, right? So we're sacrificing some of the efficiency. We're losing some more power due to this bottleneck, right? But it's acceptable because it's only localized to this volume, and it allows us to protect the circuit at the price of a little bit of power loss at nominal operation. All right. Now I want to jump to example 7.13. Oh no, sorry, not example 7.13. Example 7.12, which is an interface condition example. It's an interesting example. Let's assume that this is the coordinate system. So I have y coordinate and z coordinate. And then I have some current flowing, right? Some J1. Okay. And then there is this infinite conducting material. So, right, so there is this infinite conductor material. Those lines are at infinity. But the material has an interface. So there is an interface that's slanted at 45 degrees. So this is the material sigma 1 and material sigma 2. Right, so this is material 1, material 2. And then the question is, what is the electric field intensity just after the boundary, just after this boundary, right? So we know what J1 is. J1 is just, I mean, magnitude of J1 is given as J. It's some constant J. So we want to apply the interface conditions for the current density to find the current density just after the interface, and then use the relationship between the current density and the electric field to get the electrostatic field right after the junction. Okay, so how do we do this? Well, I mean, let's draw the interface. So let me draw like a portion of the interface, and the interface extends to infinity, right? And the interface is tilted by 45 degrees, right? So right before this is sigma 1, sigma 2, right before the interface, the J vector is moving in this direction, right? I need to divide this into a component that's parallel to the interface and a component that's normal to the interface, right? So it has to have, we need to find J1n, and then I need to find J1t. Because remember, at the interface, the normal and the tangential components transition through the interface differently. So how do I need to find some angle here, right? I need to find this angle. What's this angle? Well, I could, let me extend this like this, right? So I know that this is parallel to this. Those two are parallel, right? So I can use the parallel theorem, right? So what this tells me is that this angle should be equal to this angle, right? Why is that? Because well, how can I show that this angle is equal to this angle, which should be 45 degrees. So this angle should be 45 degrees. Another way of showing it is that you know, you see those two parallel lines here, so here and here, right? Using the theorem from Euclidean geometry, this line from Euclidean geometry, this angle should be equal to this angle, right? This follows from Euclidean geometry. So this angle should be 45 degrees, right? But this angle should be equal to this angle, again from Euclidean geometry. So we established the fact this angle should be uh, uh, 45 degrees. So what is then J1n? J1 is going to be the magnitude of J times sine 45 degrees. Sine 45 degrees is 1 over square root of 2. So I end up with J over square root of 2. And J1t is also going to be J, the magnitude of J, which is J, cosine 45 degrees. Cosine 45 degrees is again square root of 2. So I know that cosine 45 degrees equals 1 over square root of 2. Sine 45 degrees equals 1 over square root of 2. 45 degrees is the only angle where the sine equals the cosine. Right? So J1t is going to be J over square root of 2 amps per meter squared. So I found the tangential and normal components just before the interface. What about now the tangential and normal components? This is G2n and this is J2t right after the interface. Okay, what would those be? Well, we use the interface conditions, right? So the interface condition is that J1t over sigma 1 equals J2t over sigma 2. So that tells me that J2t equals sigma 2 over sigma 1 J1t. But we calculated J1t from here, right? It's this expression, which is J over square root of 2. So I end up with sigma 2 over square root of 2 sigma 1, right? So square root of 2 appears, and then I have j. So that's j2t. What about j2n? Well, j2n equals j1n. That's the interface condition for the normal component. j1n, of course, is j over square root of 2. Okay, so the norm, the j current flux density on the other side of the interface is going to be j2t equals sigma 2 over square root sigma 1j, and then j2n equals j over square root of 2, right? And those are the currents just after the interface. How do we find the problem state asks us to find the electrostatic field when we know that J equals sigma E, right? So we can use this to find E2n, which is J2n over sigma 2, which is J over square root 2 sigma 2, and then E2t equals J2t over sigma 2. J2t is this term. We divide it by sigma 2, which cancels out the sigma 2, and I end up with j over square root of 2 sigma 1. Okay, so I found A2n and A2t. So I found, right after the interface, I found E2t and E2n. What are those angles, by the way? I mean, we found that this angle was 45 degrees, right? Here, and then J1t and J1n are normal. J1n is normal to J1t, right? So the total angle should be 90 degrees. So this angle also is 45 degrees, right? So those two angles are 45 degrees, right? So if I want to express E now in material 2 in terms of the Y and Z axis, right? I need to project E2t and E2n into the y-axis and the z-axis to get the vectorial form of E, right? So so that means that E2 in the direction of y is going to be E2n cosine 45 degrees and E2t cosine 45 degrees, right? So this is going to be E2n cosine 45 degrees plus E2t cosine 45 degrees, which is going to be, what's E2n and E2t? It's going to be, there's a common element, right? What's cosine 45 degrees? 1 over square root of 2, right? So that will multiply with square root of 2 to give me 2. And the common term is that we can take out is j over 2, right? But then E2n is 1 over sigma 2 plus E2t has 1 over sigma 1, so 1 over sigma 1. So this is E2y. What about E2z, the component of E in the z direction? Right? So let me take the straight line here. So if this is 45, this is also 45, right? And this is also 45. That's the nice thing about 45 degrees, it divides evenly, right? So the z component is going to be E2n E2n cosine 45 minus E2t cosine 45, or I mean minus E2t sine 45. It's the same thing, right? So there's gonna be a minus sign there because the two components are opposing each other, right? So so E2z is gonna be E2n sine or cosine 45, it doesn't matter, it's the same thing, minus E2t. But what's important is that there's a minus now, sine 45 degrees. Right? This is 1 over square root of 2, which same deal, we'll get j over 2, but then the leftover is going to be 1 over sigma 2 minus 1 over sigma 1. Okay. So the total, the vectorial form of the electric field after the interface is going to be y hat j over 2 j over 2 1 over sigma 2 plus 1 over sigma 1 plus z hat j over 2 1 over sigma 2 minus 1 over sigma 1. Notice if sigma 1 equals sigma 2, the z component becomes 0, and naturally we end up with the field being just in the y direction, nothing changes. But if the conductivity is different between these two materials, then E2 is going to be slanted compared to E1. E1 is going to follow J, like J is in this direction, E1 will be in this direction. J gets reflected, not reflected, refracted. In the same way, E1 gets refracted, and this is the form of the electric field right after the interface. All right, thank you guys.